Welcome to this lecture series in real analysis. In this lecture, we will define the power series of a given sequence, and it is a fundamental object in real analysis. It is what allows us to define functions which are not algebraic in nature. They are truly analytic in nature. And without further ado, let us recall a few things that we need. So we will need the Weierstrass M test. It is a technical statement which we proved last time. So if we have a sequence of functions, then it furnishes a series, of course. So we have a series of functions. The Weierstrass M test gives us a sufficient condition to guarantee the absolute and uniform convergence of this series of functions, and that condition is the existence of a sequence of real numbers Mn which uniformly bounds each Fn. So each Fn is uniformly bound by Mn, and the series corresponding to Mn is convergent. So under these conditions, we can guarantee that the series of functions is both absolutely and uniformly convergent in its domain of definition, obviously. Okay, and we will also need the root test, which is also a sort of technical statement. Given a infinite series, we define this quantity, and if this quantity is less than 1, then the given series converges. If it is greater than 1, the given series diverges. If it is equal to 1, then we can't say anything. Okay. So what is the definition of a power series? Very simple definition. Fix any sequence of real numbers. The power series associated to this sequence is this formal sum. So this is just a formal sum. As of now, this is not a function, although we have an itch to substitute real numbers in place of x and think of it as a function. So we would like to think of it as something that consumes a real number and outputs a real number, where the real number you consume, you input in place of x. So we would like to think of it as a function, but there are some subtleties, and that is what we are going to discuss next. So suppose we have a power series, right? We have a sequence of real numbers an, and they are indexed with starting point being 0. So we have this power series, and we define this quantity, just like in the root test. And we declare R to be 1 upon alpha, where we have a convention that 1 upon 0 is infinity, and 1 upon infinity is 0. So this is a convention that we will use when we define R. So if alpha turns out to be 0, then R is infinite. If alpha is infinite, then R is 0. Okay, so then the statement is that this series converges absolutely whenever mod x is less than R, and diverges outside, or diverges whenever mod x is greater than R. So what we are saying is, suppose we take this interval, if we pick any point from this open interval, substitute that in place of x, then the corresponding infinite series will converge and hence will be a bona fide real number. So for each point in this open interval, minus r to r, for each point in this open interval, this thing furnishes a bona fide real number. For every point outside this closed interval, this thing doesn't output a real number because the series does not converge. And on the boundary points, we don't know anything. That depends on specifically on what these ANs are, and that's a case-by-case thing. So the upshot is, we can indeed think of this as a genuine function on this open interval. This is a function now on this open interval. Every point in this open interval outputs a real number. So this is a genuine function. Okay, so why is that? Well, this is just a straightforward exercise using the root test. All right, so here is the proof. So fix some real number x, and let Bn be defined in this way, just for convenience. This is not really a necessary step, but okay. And then we have this infinite series, this thing, this which we can write by change of notation as this, and we would like to know if this converges or not, or under what conditions on X does this converge. So to do that, we apply the root test. So this lim sup of the nth root, what is this? This by definition is this lim sup. This lim sup, which is nothing but by definition of alpha or by definition of R, this is this quantity. So by the root test, now we see that this series converges if mod x is less than R, and diverges if mod x is greater than R. Can't say what happens at mod x equals to R. So just to draw a picture, we see that the series converges in this open interval, and this R is called the radius of convergence. So this is referred to as the radius of convergence of the power series. And this region is called the disk of convergence. We would need this terminology or use this terminology frequently. Okay, let's look at some examples, at least some very basic examples. So here is the simplest power series, where, simplest in some sense, where each an is just 1. Right, so we would like to know whether or not, or what is the disk of convergence, what is the radius of convergence. But we already know, this is nothing but the infinite geometric series. We know this converges only if mod x is less than 1. We precisely know where it converges, but if you apply the root test, if you apply this theorem, you also see the same thing. You see that it converges in the region -1 to 1. Okay, and what does it converge to? Can we write down the limiting function, or can we have an alternate description of the function that this represents? This is now a genuine function from this open interval to the real numbers, but can we explicitly or more simply write down that function? Yes, we can, because we know that this limit is nothing but 1 upon 1 minus x, under the assumption that mod x is less than 1. So this we have seen many times. This is the geometric series, so we know this, and we can draw a graph of it. So the graph of this thing in this open interval looks like the way I've drawn. As you approach, as you go closer and closer to 1, the value will blow up because the denominator will become smaller and smaller, but still remain positive because we are approaching from this side. But as you go towards the left side, it doesn't really give an idea why the convergence is breaking down as you approach -1. This graph is not giving the idea why the convergence of this is breaking down as you approach -1. But we know the convergence break down definitely. Okay, let's look at another example which is more well behaved in some sense. So this time our power series is this. So if you want to express this in terms of ANs, you would say that AN is 0 if n is odd and 1 otherwise. So that's this power series. And again, we know, by either you can apply this, you get the convergence happens in the unit in this open interval -1 to 1, and doesn't happen outside this closed interval. The same root test will give you that. And we can also observe that this is nothing but the geometric series with x square being the common ratio. So we know what this converges to and in what region. So this would be equal to 1 upon 1 minus x square. 1 upon 1 minus x square if mod x is less than 1. And yeah, what is its graph? Its graph looks like this. So as you approach minus 1 from the left, it blows up to infinity. As you approach 1 from the left, if you approach minus 1 from the right, it blows up to infinity. And if you approach 1 from the left, it blows up to infinity. And in this region anyway, it's not defined. So here we do see why the breakdown, happens beyond this disk of convergence. That is kind of very well suggested by the limiting function. There is a singularity here, so to say. But in the next exam, something strange will happen. So this time, this is our power series, and you can, you can write it as this way. So again, if you apply the root test, you will see that its disk of convergence is the same thing, this interval. But we also know that this will be equal to 1 upon 1 plus x square, because this is another geometric series, if this is the case. Right? So just using the geometric series nonsense, we get that the given series is equal to this, provided here. And what does the graph of this look like? Graph of that looks like this. And it is giving no hint as to why the convergence of this is breaking down beyond the point 1, beyond the point minus 1 and beyond the point 1. This graph is giving us no such hint. And this is why are we not able to see the breakdown of convergence, is because we are confined to real numbers. If we look at it from the lens of complex numbers, then we would see why the convergence breaks down. For example, if you substitute the imaginary number iota in place of x, you will see a 0 in the denominator. So you can ignore what I'm saying, but I'm just trying to tease some complex analysis here, and this you can take as an invitation to complex analysis. So the full picture is that you shouldn't just restrict your attention to the real line, but you should think of it as a function on the complex plane, and then ask the question, what are all the points from the complex plane that you can plug in place of x and still retain a convergent thing? And all of that we haven't discussed because we haven't talked about complex analysis at all. But to actually see why the convergence, or to get some idea as to why the convergence breaks down here beyond the disk of convergence, is something that would call for the complex plane to come into existence. Anyway, ignore that comment if you didn't follow. All right, great. Now for one last thing. So we just saw that there is a disk of convergence within which the power series converges and can be therefore thought of as a function there. But then naturally we would like to ask if the convergence is uniform. And the answer it almost is. So suppose we have a power series and R is its radius of convergence, and assume that R is a positive real, so that there is some genuine neighborhood around the origin where the power series converges. So then we would like to say that fix an epsilon greater than 0, the power series will converge on the the epsilon truncation of the disk of convergence. What do I mean? We have the disk of convergence. This is R plus this is R, this is minus R. And what are we doing? We are truncating the region of discourse. So this point is R minus epsilon. This point is minus R plus epsilon. And we are saying that within this region, within this truncated region, the convergence is uniform. So if you restrict this series or in other words, the sequence of partial functions furnished by this series, and restrict all of them to this region, then this sequence of functions converges uniformly to the limit that this function is. Okay, so why is that? Well, this will be an application of the M-test. So the M-test we recalled in the beginning, and we'll just use it. So for all x in this truncated region, we have that the nth term of the of the series is at most this much, obviously, simply because x has been chosen in this truncated region. So this inequality holds trivially, and this thing we will refer to as, we will declare this to be equal to m sub n. That's the definition of mn. Okay. Now, what are we interested in? We're interested in this series of functions, right? You can think of it as a series of functions, namely the nth partial sum, fix a capital N. The capital nth partial sum is just this genuine function, which is a polynomial in fact. It is defined for every real number, but we are only restricting our attention to this region. Okay, great. So, yeah. So what does the M-test say? The nth guy, let's call the nth guy fn. So this function, let's call it fn. Let me write fn of x. Fn is a function defined here, which at x takes this value, and what we have seen is, the way we have defined mn just says that fn is uniformly approximated or uniformly bounded by mn, not approximated but bounded by mn. So if we can show that this summation is finite, meaning the series mn converges, then by Weierstrass M-test we would be done. But does it converge? So we are asking if this thing converges. We know it does converge because in the previous lemma we said that the series converges absolutely in its disk of convergence. Perhaps I did not emphasize that, but I had written it. Converges absolutely. It's very important that the convergence is absolute. And the same proof furnishes the absoluteness of convergence. So here I should have said it doesn't just converge, but it converges absolutely. So because the convergence is absolute in the disk of convergence, this is finite. And now just apply the M-test and we are done. Okay. It's a very simple proof. I don't know if I confused you by my exposition, but it's nothing. Just think of the M-test and you can write down the proof by yourself. Use the fact that power series converges absolutely in its disk of convergence. Not just in the usual sense, but in a stronger sense, namely absolutely. And one example, or rather an exercise, if you will, the geometric power series, if I may call it that, this does not converge uniformly in its entire disk of convergence. It will converge uniformly in any truncation of it, as the theorem just proven shows, but it doesn't converge uniformly in its entire disk of convergence. And as we saw, the graph of the limiting function looked like this. As you approach 1 from the left, there was a blow up in the limit, so that is what you can just use to prove this non-uniformity of convergence. It's not a difficult exercise. Okay, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.